Welcome back. This video is part 2 of our optimization sample problem. If you haven't watched the part 1, do click the link down below. So today we need to find the maximum area of a rectangle bounded by the function negative x squared plus 4 and the x-axis. Here is the graph. The red line represents the function negative x squared plus 4. We notice that when the rectangle is closer to the x-axis, its area is less. When the rectangle is closer to the y-axis, its area also less. Denotes that the maximum area possible is located somewhere in this blue rectangle. Let us assign the length and width as the following. As you remember, the area of a rectangle is represented by area equals length times width. Our main goal is to define the area into a single variable function. First, we notice that our function and our rectangle is even. What do I mean by that? That whatever we have on the right hand side is same as on the left hand side. So this rectangle is same as this rectangle, and the whole rectangle is same as the twice of the area of this rectangle. Now we can denote that the whole area is same as twice the width times the length of this rectangle. The width is same as the input x, and length is same as the function f of x. So the area becomes 2 times x times f of x. And our f of x is same as negative x squared plus 4. And distributing the 2x, we have negative 2x cubed plus 8x. Now we can take the derivative because we already defined the area in terms of single variable x. So we do a simple reduction of power. Derivative of negative 2x cubed is 2 times 3 is 6, negative 6, and x to 3 minus 1. So we have negative 6x squared plus the derivative of 8x is 8 equals 0. We set to equal to 0 to find the maximum. Transfer 8 to the other side and divide all sides by negative 6 become x squared equals 4 over 3, and take square root, we have x equals square root of 4 over 3. So we keep this form for now. We have already the value of x, which is represented by the width. So we need to find the length, represented by the f of x. So we need to substitute the values of x in our function. So our function is negative x squared plus 4, same as the f of square root of 4 over 3 equals negative square root of 4 over 3 square plus 4. So radical cancel, we have negative 4 over 3 plus 4, and 4 same as 12 over 3, and negative 4 plus 12 is 8 over 3. Now that we already have the value of our length, after plugging in square root of 4 over 3 in our function, and that is 8 over 3, now we can find the area of the whole rectangle, represented by a equals 2 times the width times the height. So square root of 4 over 3, the numerator part is just 2 over square root of 3. So we have 2 times 2 square root of 3 times 8 over 3. Numerator is 2 times 2 is 4 times 8 is 32. The denominator is square root of 3 times 3 is 3 square root of 3. And rationalize because we don't like the radical under the denominator. So we both multiply square root of 3, and this become 32 square root of 3 over 9. Approximately 6.1584. So the maximum area possible of our rectangle bounded by the x-axis and our function is 6.1584 units. Moving on to our final problem, we have a right cone of height of 6 and radius of 3. We need to find the maximum volume possible of an inscribed cylinder. So here is the graph of our cone and our cylinder. The green one is another cylinder and the yellow one is another. So we need to find the maximum volume possible. The volume formula of our cylinder is V equals pi r squared h. Like what we do in our previous problems, how we gonna define the volume in terms of a single variable? We notice that the edge of our cone represents a straight line rotated at some point. So let's say we have a line that passes through 6 and 3. When this line is rotated about the y-axis, it forms a cone of the height of 6 and radius of 3. So this cone is same as the rotated of this line about the y-axis. Now we need to find the equation of this line. The equation of line is y equals mx plus b. Since our line passes through 0, 6, then its y-intercept is 6, so we have y equals mx plus 6. Now what is the value of m? Since the line passes through 3, 0, we can input the 3, 0 in our equation. We have 0 equals m times 3 plus 6 and become m equals negative 2 by transferring 6 to the other side and dividing by 3. So our equation of our line is f of x negative 2x, the slope negative 2, and the y-intercept plus 6. Now the cylinder radius depends on the input x and the height depends on the function f of x. Now the volume of cylinder is denoted by pi x squared f of x. The x represent the radius and the f of x represent the height. Our f of x is negative 2x plus 6, and apply distributive, we have pi times negative 2x cubed plus 6x squared. Since pi is constant, it remains there, and the derivative of negative 2x cubed is 2 times 3, negative 6, and x to 3 minus 1 is 2, and the derivative of 6x squared is 6 times 2, 12x. We set equal to 0 to find the maximum. Pi is constant, so we can cancel and factor out negative 6x. So we have negative 6x times x minus 2 equals 0. So the solution are x equals 0 and x equals 2. For maximum, we take x equals 2 and substitute to our volume formula. Substituting x equals 2 in this equation, we have negative 2 times 2 cubed plus 6 times 2 square times 5. So this one is negative 2 times 8, negative 16, plus 6 times 4 is 24 times pi. So the maximum volume possible of our cylinder is 8 pi unit cube. Okay guys, that's all. Thanks for watching.